Hello everyone. Let us start off with the topic of quadratic equations now. To begin with, we will review some of the basic concepts that most of us might be familiar with already. A quadratic equation, as we know, is of the form ax square plus bx plus c equal to 0, where a, b, c are real numbers and the leading coefficient, that is a, is not equal to 0. Now, unless otherwise mentioned, we will always assume that the coefficients a, b and c are real. As to the methods to solve a quadratic equation, we are aware that there are typical three methods that we use. That is, first is we try to first factorize the quadratic expression if it's possible, which directly gives us the roots. Otherwise, we complete the square and then we get the roots of the equation. And lastly, we have a direct formula that gives us the value of x, which is nothing but minus b plus or minus root of b square minus 4ac whole upon 2a. Now this quantity b square minus 4ac is called as the discriminant, which is denoted by either d or delta. This is a very important parameter because the discriminant tells us about the nature of roots of the quadratic equation. So let us see how the discriminant distinguishes between the different types of roots. So here this chart gives us that particular classification. Now on higher level we have two possibilities, that is either delta is less than 0 or it is greater than or equal to 0. If delta is less than 0, then the roots are not real, that is they will be the complex conjugates of each other. Simply because the delta appears inside the square root in the quadratic formula. So therefore, if we have a square root of a negative number, it will naturally have the imaginary component. Now coming to the real roots, that is when delta is greater than or equal to 0. If we consider the one part of that is delta equal to 0, which would lead to the roots being equal to each other. On the other hand, if delta is strictly greater than 0, then we'll have the real roots but they will be unequal, that is the distinct roots. Now there might be a further special case, that is if delta happens to be a perfect square and the coefficients a, b and c are rational numbers, then the roots also will be rational. Whereas if delta is not a perfect square and a, b and c being rational numbers, the roots will be irrational numbers. Let's move ahead and see the relationship between the roots and the coefficients of the quadratic equation. So if we denote the two roots by say alpha and beta of the quadratic equation ax square plus bx plus c equal to 0, then the sum of roots, which is nothing but alpha plus beta, is given by minus b upon a. That is, you can see the ratio is of the x coefficient and the x square coefficient. Whereas the product of roots, that is alpha beta, is given by c by a, that is the constant term divided by the coefficient of x square. If you want to know the difference of roots, that is absolute value of alpha minus beta, so we are ignoring whether alpha is bigger or beta is bigger. So in that case, we can use the identity, which is alpha minus beta the whole square is equal to alpha plus beta the whole square minus 4 times alpha beta. And as we have already found out the value of alpha plus beta and alpha beta, so substitution will give us the value of alpha minus beta or beta minus alpha, the positive difference. Now moving on, we will see how to evaluate some expressions which are symmetric in alpha and beta. So by symmetric we mean even if you interchange alpha and beta, the overall expression remains same. So here are some of the examples. The intention here is to express these particular expressions in terms of the sum and product of alpha and beta, as we have seen previously. Now alpha square plus beta square, as we know, can be written as alpha plus beta whole square minus 2 alpha beta. So therefore we see that once again we got the sum and the product. Now moving ahead, if we want to write alpha cube plus beta cube, then we will use the cubic identity, that is alpha plus beta whole cube minus 3 times alpha beta into alpha plus beta. So once again we see that we got the sum as well as the product of the two roots. Moving ahead, if we have 1 upon alpha plus 1 upon beta, on cross multiplication and simplifying we get beta plus alpha upon alpha beta, which is the sum of roots upon product of roots. And lastly, if we have reciprocals of squares added, then that once again gives us the similar expression, that is beta square plus alpha square upon alpha square beta square, where the numerator can be once again rewritten as done in first step, the first example above. So which is alpha plus beta whole square minus 2 alpha beta, and the denominator is nothing but basically the square of the product, is alpha beta the whole square. So this is the way in which we can evaluate any such expression in alpha and beta once we know the sum and product of the two roots. It's not only applicable to the quadratic equation, but we can generalize the relationship between roots and coefficient of any polynomial equation in this particular way. Now let's consider if there is an equation which is as shown here, which is a polynomial equation in x, and since it's of degree n, it will have n roots, that is denoted by alpha 1, alpha 2, alpha 3 up to alpha n. Then sum of the roots, that is alpha 1 plus alpha 2 plus alpha 3 plus so on up to lastly alpha n. This will be given by minus of a1 upon a0. So here if we see, it is this particular expression, a1 on a0. Now suppose we want to take the sum of product of two roots taken at a time. So that means it is alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 1 alpha 3 and so on. So it would cover all the possible products of the two roots taken at a time. So this will be given by a2 upon a0, which is nothing but the next coefficient divided by the leading coefficient. Now here we observe that the sign is positive. Now if we take the sum of product of three roots at a time, that is alpha 1 alpha 2 alpha 3 plus alpha 1 alpha 2 alpha 4 and so on till we cover all the possible products, this will be given by minus a3 upon a0, which is nothing but the next coefficient in. So in this way we can continue and generalize till lastly we arrive at a point where we take the product of all the roots. There will be only one such product since we have covered all the roots. So that will be given by minus 1 raised to n a0 upon a1.